So chapter 19 has been divided into 4 topics and 4 parts. I must say the first part we had done the other day, but as a review, we had talked about the quantity of heat that is either gained or lost by an object when it gets heated up or it cools down. We've seen this formula. H is the heat, the quantity of heat, M is the mass in kilograms, C is a constant called the specific heat capacity. Delta T is change in temperature. So whenever an object gets heated up or it's cooling down, this is the equation that you will use. Again, take note that temperature's always got to be in Kelvin, but in this case, because you're dealing with change in temperature, it could be in Celsius. You understand that, right? Okay. So each material has a constant which is called the specific heat. And if the specific heat is high, like for example, water has one of the highest specific heats, if not the highest, which means it gets heated up slower than the others, isn't it? If the specific heat is high, then it's going to take a lot of heat for it to get heated up. That's why even in summer, if you jump into a lake or a pool of water, it's not so hot. The sun has been shining into it for hours and hours, but the temperature has not gone up so much. It's going to be considerably cooler than the atmosphere, even at noon, right? The reason is the specific heat of water is really high. Now compare that with the specific heat of a metal, like copper, I think is 385 or 390 joules per kilogram per Kelvin. It has a small specific heat, so the change in temperature is going to be that much faster. So that's what you have to understand from that formula. Now going to the second case, some materials undergo phase changes, right? Change in phase, where they go from solid to liquid, liquid to gas. In that case, there is no change in temperature, and the formula that you would use is H is equal to mass times the latent heat. And the latent heat could either be latent heat of fusion or latent heat of vaporization, depending on what's happening. If it goes from solid to liquid, it's latent heat of fusion. If it goes from liquid to gas, it's latent heat of vaporization, right? So you have to think about what process is going on and then use the formula. Has anybody heard about a process called sublimation, where it goes directly from a solid to a gas? And what's the opposite of that called? Deposition. That's right, deposition. I've not heard that answer many times. Deposition is the opposite process. Okay? So those are the 2 formulas. And I just forgot to tell you that if you mix a hot object with a cold object, heat lost by the hot will be equal to the heat gained by the cold, which you have to use depending on what the problem is talking about. That brings us to the second part. Remember that, what we're looking for is to get energy from a system. So as you see on the whiteboard now, consider that you have a container with a gas in it. That's what I've tried to represent. Okay, a container with a gas in it. So there are molecules flying about, right? Millions of molecules flying about, and they have what we call internal energy. And that internal energy is of 2 types. 1, kinetic, and 2, potential. Because there is intermolecular attraction between the molecules, isn't it? So it has potential energy, and it's moving, so it has kinetic energy. The total of the 2 is called internal energy. And what happens if heat enters the system? What happens if heat enters the system? What happens to the internal energy? It'll go up. If heat leaves the system, the internal energy will go down, right? So there could be a change in internal energy. But when this change takes place, we would always see, what are we trying to look at? We're trying to look at how much energy is there in the system. Why? Because we are selfish and we want to use it. That's the whole idea. We want to use how much energy is there in the system. Now, to use it, don't we have to know how much we already have in there? But there is a problem. You can't measure the energy directly. No. But there are some quantities that you can measure. 4 quantities: pressure, volume, temperature, and entropy. Now, these 4 quantities are called the thermodynamic coordinates: pressure, volume, temperature, entropy. And why do we need to measure these? So that we can estimate the amount of energy in the system. Is that clear? Okay. But when you look at these 4 coordinates, I'm going to define 4 types of changes, as you can see, where in each change, one of the coordinates is a constant. Now, that's easy to understand. But before I get there, let me just try to get an answer from you. Suppose I have a container with water here, and I'm just heating it. What are the coordinates that are constant there? Well, I thought when you heat a liquid, its volume changes. That's what I thought. The volume of the container also changes, though negligibly, right? So go back to that question. You are heating it in an open container, trying to give you a clue now. In an open container, you're heating it. Which coordinate is a constant? The pressure is the atmospheric pressure, right? So the pressure could be constant. Now, let's take another case where you have kind of a cylinder with a piston in it. Can you imagine that? A closed cylinder with a movable piston. But right now, the piston is fixed. And you have a gas inside. Now, if the piston can't move at all, and you heat it, what's going to be a constant? The volume is going to be a constant. Correct? Go back to these 2 examples. In both these cases, temperature was changing. Is that clear? Temperature was changing. Come on. Now, there is a 4th one called entropy. That is like love. It's abstract, can't be defined. It's true. In chemistry, you have studied that entropy is a measure of disorder of a system, haven't you? If heat enters the system, what happens to the disorder of the system? Increases, which means the entropy also increases. Which also means that if you remove heat from a system, it gets more ordered. Therefore, its entropy is going down. And what is happening to the temperature? When you remove heat, what's happening to the temperature when you remove heat? It's going down. And what's the lowest temperature that can be reached?
0.
Absolute 0. And according to the 3rd law of thermodynamics, at absolute 0, the entropy becomes 0. Now, before I give you the 1st law and the 2nd law, I give you the 3rd law. It's easy to understand because you've removed all the heat in it. And can you visualize the molecular motion?
Very slow.
Nothing is moving, actually. No movement. At absolute 0, there'll be no movement. The molecules are at standstill. No internal energy. No entropy. I hope you got that. So now I gave you an idea of all the 4 types of changes. Now let's look at them one by one. Graphs are really useful in representing changes. And the graph that we're going to use here is between pressure and volume, as you're going to see. Now, those are the 4 coordinates. You have volume on the x-axis, pressure on the y-axis. And let me set up all the 4 first. And all the 4 are similar in that the x-axis is volume, the y-axis has pressure. All right, look at those 2 changes because 2 have come up. You don't know what type of change that is. But if you take a close look at this carefully, you will see that one of the graphs has a greater slope. Which one? I call this first, and this is second. Which graph has a greater slope? Second. The second slope, which has a greater slope, is called an adiabatic change. An adiabatic change. That is where the entropy is constant, okay? It is called an adiabatic change. The slope is greater. The first graph that you see there is called an isothermal change. Temperature is constant. The third one that's coming up and the 4th are dead easy to understand. And if you can't tell me what is constant in the 3rd and the 4th, you are more than asleep. If you cannot tell me what's constant here, of course, remember it's pressure here. You only see a part of it. pressure on the y-axis. So what's constant here? Pressure. It's called an isobaric change. Pressure is constant, definitely, right? And here, volume is constant, so it's called an isovolumetric change. Isovolumetric. The word iso means the same. So now let's go one by one. This is an isothermal change, temperature is constant. Adiabatic change, entropy is constant. I would call it isentropic change, but the textbook does not. So again, isothermal, isentropic, isobaric. Why baric? Do you know that there is a particular unit of pressure called millibars and bars? That's why it's called isobaric, B-A-R-I-C. And this is isovolumetric. Sometimes I have seen textbooks use isochoric. So, same thing, means volume is constant. Those are the 4 types of changes. Now, before I go further, I want to ask you one thing. And just to make sure that you're listening. We're always looking for mathematical representations, right? So who here can give me an equation that represents an isothermal change? Now, remember there are... And the whole field of thermodynamics is dependent on 4 laws, and the first law, as illustrated here, talks about a system into which heat flows in. dQ is the amount of heat coming into the system, and this system may be a gas contained in a cylinder with a movable piston, and a part of this heat is used for the gas to expand. Another part is used for the increase in temperature. So the heat entering is used up in 2 ways, and the change in internal energy is going to be the difference between the heat entering and the work done by the system for the expansion. So since the work done is P times the change in volume, and remember that P is the constant pressure, the first law of thermodynamics can be written in this way. Change in internal energy is equal to the difference between the heat entering the system and the work done by the system. And dQ is CV dt, where CV is the molar specific heat at constant volume. Now that's supposed to be dE actually. Okay, so dE is CV dt. I'm going to change that to dE. And another relation that's really important is Cp minus Cv is equal to R, where if you take the difference in the molar specific heats, you will get the universal gas constant. The equation for the isothermal change is the Boyle's law equation, Pv is equal to constant, because Boyle's law is defined with the condition that the temperature is constant. Okay, so that's the equation for an isothermal change. Now to find the equation for an adiabatic change, remember that an adiabatic change is one that does not involve any transfer of heat. That means no heat enters the system and no heat leaves the system. And when we do the math, which I'm not making you go through, finally you get this relation, PV raised to gamma is equal to constant. Or you can also use TV raised to gamma minus 1 is a constant. So those are the 2 equations for an adiabatic change. Pressure times volume raised to gamma is constant. Now remember that gamma is the ratio of specific heats, Cp by Cv, and since Cp is always greater, gamma is going to be greater than 1. For a monoatomic gas, gamma is 1.67. For a diatomic gas, it's 1.4. And a polyatomic gas, it's 1.33. So those are the values of gamma. And if the problem is talking about air, and because air is more a mixture of diatomic gases, gamma would be 1.4 for air. Now there are three ways for the transfer of heat in materials: conduction, convection, and radiation. A conduction usually takes place in solids. It's a slow process, and it is due to the increased molecular vibration. Now consider that you have a solid with temperatures on the two faces being T1 and T2. Heat will be conducted across the material from the higher temperature to the lower temperature, and the heat conducted every second will depend on, number one, the material, number two, the area of the phase, three, the difference in temperatures between the two surfaces, and also on the distance or the thickness of the material. So if Q is the quantity of heat that's conducted in T seconds, then the formula is Ka T1 minus T2 divided by the thickness, which is D. K is called the thermal conductivity. It's a constant for each material. Its unit is watt meter raised to minus 1 Kelvin raised to minus 1. Now that's the formula that you need to know for conduction. And when it comes to radiation, radiation is a process that does not require a material medium, and this is the process by which the sun's heat reaches the earth, traveling through miles and miles of space. And radiation depends on the nature and color of the surface, depends on the surface area, and it depends most on the temperature of the object. When you put all those factors in, Q is the quantity of heat radiated in T seconds. The little e here is called the emissive power. For a white polished object, the emissive power is 0, while for a dull black surface, the emissive power is 1 or 100%. A is the area of the surface. Sigma is a constant called Stephan's constant of value 5.669 times 10 to the negative 8. T1 is the temperature of the object. T2 is the temperature of its surroundings. Alright, so as shown in the diagram, T1, that's the temperature of the object, and T2 is the temperature of its surroundings. And sigma is the constant. Its unit is watt meter raised to minus 2 Kelvin raised to minus 4. Again, E is the emissive power that takes values between 0 and 1. 0 for a bright polished object and 1 for a black object. A is the surface area, T1 temperature of the object, and T2 temperature of the surroundings. So I hope you go through all these topics from, that is chapter 19. Thank you.